Hi, welcome back to the second part of the pulleys lesson. In this part, we'll see an example of analyzing a pulley system. So in this example here, we have two pulleys, pulley A and pulley C. Pulley A is fixed because it's pinned to the ceiling. It's not moving with the movement of the load that we're trying to lift or hoist. But pulley C is a movable one. It was a moving pulley because imagine if you pull the force P here, the pulley C will move up with the load that you're trying to lift Q. So we have two pulleys, and then we have two pulley cables. The first one is ACB, so if you can trace it, A from the middle of pulley A to around pulley C to support or the pin B. And then you have the CAD cable, and CAD here is from CA to D. So from the middle of pulley C around pulley A to the point where P, the load, is applied, D. We know that as an input P is equal to 750 Newton, and now the problem asks for two things: the tension cable and the tension force in cable ACB or cable AB, and the magnitude of the load that you're trying to lift here, Q. So the way to deal with this problem is to analyze the free body diagrams of the two pulleys we have in the system. So imagine we'll split them, but before that, it's good also to visualize the cables. So I'm using different colors here. So CAD cable is the blue one, and ACB is the red one. And using colors might help you here so you can trace the forces, because we know in every one of these cables or any point along their length, the force is the same. The internal force is the same. The edge forces are the same, are equal. So that will help us to trace the equal forces along each one of these cables. So now it's the time to draw the free body diagrams of each. So A's free body diagram and C's free body diagram. And again, you can relate the cables and their colors to the original problem. So if I start with the point where I apply the P, the input force, P, 750 Newton, I see that at the end of this cut that I'm doing at the end of this cable, CAD, the force kind of flows through the cable, 750 also. And this same cable is shown on the free body diagram of the C pulley, and it also feels 750 Newton. So the force that I'm using to pull the load, 750 Newton going down, it flows this through the cable CAD. The other cable feels another force, and I will call it here TAB. Should be TACB, but just making it short, TAB. It's unknown, so and usually cables act in tension. So if a cable is under compression, it will not actually be helpful. It will just will not be functioning as it's supposed to. So here, as a tension force, meaning that the force is going out of the element. So here you're feeling tension force and going kind of downward right in the free body diagram of pulley A, and it's reversed on, it's the same cable, but I'm cutting it on another free body diagram, so it's equal and opposite. And on the right side of the free body diagram of pulley C, also I have TAB. So kind of the cable is tension along its length with the same equal value. So now I can kind of visualize the flow of forces through the cables. One cable, I know the force through it because I know the force at the end of it, 750 Newton. The other one is unknown. Q is another unknown. And another unknown, don't forget about it, because now it's kind of the system is flying in the air without considering the reactions at A. So pulley A is hinged, and this hinge is supported by the ceiling. So we'll learn in 2D equilibrium that in hinge supports you have two reactions, AX and AY following the X and Y coordinates. So now I have complete free body diagrams, two free body diagrams. Now to summarize, I also need to show here the directions of these forces. So for every free body diagram, I have two equilibrium equations. Because this is a 2D system, so I have the sum of forces in X and sum of forces in Y, both of them are equal to 0. So let's see how many unknowns I have in every free body diagram. So the free body diagram of A, I have 3 unknowns. So kind of it's bad news because I have 3 unknowns and 2 equilibrium equations to apply there. I can't really jump right away into the free body diagram of pulley A. But for pulley C, good news. I have 2 unknowns, only 2 unknowns, which matches with the 2 equilibrium equations I can apply there. And in this case, it's kind of a must. We have to start with analyzing free body diagram of pulley C. So now focusing on only pulley C. So kind of I'm drawing here, the focus now is on this free body diagram. So if I focus on that, which equation I should apply first, sum of forces in X or sum of forces in Y. It doesn't matter really, but it's better to apply the equation that will give you right away one of the unknowns. So if I look, if I apply the sum of forces in Y, components of TAB are applying in the Y direction, and Q force, the load here, is also in the Y direction. So 2 unknowns, 1 equation will not be enough to solve right away for these one of these 2 unknowns. But if I look at the sum of forces in X, Q is a pure vertical force, so it's only in the Y. There is no X component for it. So TAB will have X components. It's by itself in 1 equation. I can solve for it. So examine the problem. Check which equation you will apply, which will be faster for you to solve the problem. So sum of forces in X is equal to 0. That's the step I'm deciding to take here, and picking the positive direction to be going to the right. You can see here I'm taking the components of TAB, the 2 forces going right and left with the angles, and also taking the X component of the 750 Newton going to the left. So solving with that, I can see here that TAB is positive, just confirming that the direction is correct, and it's this value here, 1293 Newtons. So kind of I'm done with requirement A. Then requirement B is the second unknown in this free body diagram, force Q. And I can do that by the sum of forces in Y is equal to 0. My positive direction is upward. And just taking this here, deleting it. Again, the focus for us is this free body diagram. And you can see here, I'm plugging right away TAB is equal to the value that I got. It's positive, so I'm plugging it with the same sign I got before. The direction is correct, so I'm sticking to it. And the only unknown I have is Q, so solving for Q, I will have 2220 Newton, the load that I can lift with an input force of 750 Newton, which is a good observation to make here, what we call the mechanical advantage. So the mechanical advantage is the ratio between how much is the output force over the input force. So the ratio here is more than 1, is actually close to 3, which is indication of how efficient the system is. So kind of with every Newton I put in, I get 2.96 Newtons out. So it is a good system. Can you improve it? You can by adding more pulleys and making more complicated kind of pulley system. So that concludes the example here. Again, my advice is to trace the pulley cables so you visualize and be able to trace the forces along their length. It's equal force in every one of them. try to analyze the free body diagram of each pulley, but still relate these pulleys together, like we did in this example, and also make sense at the end of the pulley system, kind of making a conclusion. What's the mechanical advantage that you can end up with? It didn't ask for it in this problem, but it's good. As engineers, we're always curious about the efficiency of the things we design. Okay, thanks for watching. I will see you in other videos. Take care.